Hello, everyone. I'm Chong from Princeton, and today I'm going to present our ObjectSeeker paper, a certifiably robust object detection technique against patch hiding attack. My collaborators are Alex, Saeed, and Prateek. I will start the talk with the problem setup. First, what is the patch hiding attack against object detection? Given an image, an object detector needs to predict a list of bounding boxes and a class label to detect every object. A patch hiding attacker here is going to corrupt a local image region, which we call a patch region, and then optimize the patch content to hide the object from being detected. In this example, all boxes are gone, though we humans can still recognize every object. And this imposes a threat to critical perception systems such as autonomous vehicle. And note that this attack is realizable in the physical world. That is, the attacker can print and attach the patch to the physical object, and then image taken from that physical scene can become malicious. Here are more physical world attack examples. Stickers can hide the stop sign. The adversary t-shirt can hide the person on the right. A patch on the wall can hide all items on the table. And in our paper, we aim to defend against patch hiding attacks. And our defense objective is to achieve certifiable robustness. The idea is that given a defense model we build, certain objects on the input image, and the threat model, we aim to generate a certificate which says the model can always detect the object, no matter what a white box adaptive attacker within the threat model does. The attacker can know everything about the defense, including the algorithm, parameters, model weights, and model architecture. And our threat model further allows the attacker to place a patch of a certain size at any valid image location and to have any malicious content. And our robustness certification needs to account for attacker with all this different flexibility, and we need to try to always detect the object. In this talk, we are going to focus on the one patch attack setting, but in our paper, we discuss multiple patches. Now we can discuss the ObjectSeeker algorithm. The core idea is we want to mask out the entire patch to neutralize the adversary effect. Then we can use any undefended model to safely detect the object. The challenge, however, is how can we mask out the patch when we do not know where the patch is and when we do not know the shape and size of the patch? Our solution is to add a set of masks. Given an image, we can consider masks with different shapes and size, and we can apply them to different image locations. The intuition is that if some mask from our mask set removes the entire patch, we can detect the object on image without adversary pixels. And once we detect boxes on different masked image, we can aggregate them for the final output. And I will next discuss the details of these two steps. Start with the masking. The major question here is, without knowing the patch shape, size, and location, how can we generate a mask set such that some masks can remove the entire patch? We proposed an image half masking algorithm. Given the image, we will select a set of lines, for example, k evenly spaced vertical lines. Then each line is going to divide the image into two halves. We mask out one half and perform vanilla detection on the remaining half. Then we will repeat this process for different image halves, for example, masking out the right half as well, and also repeat this for different lines. This operation allows us to detect different parts of the object and lays a foundation for robustness. And of course, we can consider different lines, for example, horizontal lines. Then we will mask out different parts of the image and detect different parts of the object. One intriguing property of this masking strategy is that the only input parameter k, the number of lines we want to use, does not depend on any patch information here. That means we can use a fixed mask set for different attackers who use different patch shapes, size, locations. For example, for this patch at the corner, if we consider a mask set generated by 3 vertical and 3 horizontal lines, then we can detect 3 different parts of the object. Then if we consider a patch at a different location, the same mask set still allows us to detect the modify. And again, if we consider a patch of different size and shape, the same mask set still helps us to detect the object. We note that this patch-agnostic property is very useful in practice because we no longer need to worry about underestimating the attacker's capability, such as the patch size. And this patch-agnostic image half masking is the core operation and also the first step of our algorithm. Next, the second step. The reason why we need box aggregating is because the same object can be detected multiple times on different images. Here, we can see we have 2 boxes for the Mahloujifar. Note that duplicate boxes are false positive errors. So the question here is, how can we safely remove duplicate boxes? We have 2 sub-steps, box filtering and box unionizing. Now imagine there is a clean image without any adversarial pixel. If we use this mask set, we might detect 8 different boxes for one single object. In order to remove those redundant boxes, first, we ask the model to make prediction on the unmasked image. We get a box, and we call them base box B. Then we are going to identify and remove any masked box M that are similar to the base box B. And the similarity is measured by a score function. There are many different design choices. One option I discussed here is we can calculate the area of the box intersection divided by the area of masked box. And this captures how much of the masked box M is covered by the box B. In this example, we will find that the similarity score for all masked boxes are high, and then we can effectively remove all of them. Then, if we take the base box plus any remaining masked box as the final output, we have successfully only output 1 box for 1 Mahloujifar. Now let's take a look what happens when there is a patch. The patch might remove the base box and may also remove some of the masked box. Now there is no base box. That means no masked boxes can be filtered, so still we have duplicate boxes. To address this issue, we are going to unionize any remaining masked box before the final output. Specifically, we're going to perform distance-based clustering using the similarity score, and then we retain 1 representative for each cluster. One strategy for representative selection is we can calculate the mathematical union for all masked boxes, and we discussed all options in the paper. And this operation helps us to merge the redundant box. And that's it for the algorithm. Let's have a quick recap. Given an image, masking, we get the masked boxes. Get vanilla prediction, we get the base box B. Then we are going to aggregate the masked box M to get the box MA. The final output is the base box B plus the box MA. Now the remaining technical question is, how can we perform robustness certification? Intuitively, the robustness of ObjectSeeker comes from the masking operation. So if we can detect a high-quality masked box on a masked image without adversarial pixels, then this box is not controlled by the attacker and is likely to survive all the operation and become part of the final output. And in our paper, we develop a math formula to determine the box quality, and we prove the correctness of the formula. And our certification with this formula, we only need to look for if we can detect any high-quality boxes. The certification procedure works as follows. First, we get a patch region that we want to certify the robustness for. For example, a corner region. Then we are going to find all masks from our fixed mask set that can cover this entire patch region. Then we make a prediction, gather all boxes, and check the box quality. If there is no high-quality box, the certification fails, meaning that attacker might bypass our defense using this patch region. If there is high-quality box, then that means our defense is robust for this patch region. Then we are going back to the beginning to consider any more patch region we want to certify. For example, it could be a region at a different location. And once we have considered all possible patch locations, patch regions, and the certification never fails, that means we have the certified robustness. We can always detect the object no matter what an attacker does using any of the patch region. And in our evaluation, we will use this certification procedure and calculate the fraction of objects for which the certification succeeds. And we report this number as the certified recall for robustness evaluation. In addition to that, we also report the average precision for clean performance evaluation, just when there is no attack. And the average precision is the conventional metric for undefended model. Then let's take a look at the result. We discussed the AP and certified recall for different threat models. We consider 3 different object detectors, undefended models, and detector guard, that is the only prior defense, and our object seeker. We consider 2 benchmark data sets, VOC and COGO, in this talk. So first, look at the average precision for clean performance. We can see that object seeker only incurs a very small drops in clean performance, just about like 1%. And this observation holds for different data sets. And second, for the robustness, this is the performance for the detector guard, and this is object seeker. We can see a significant improvement in robustness that is 2 times for the VOC and 3 to 6 times for the COCO. And all these results demonstrate the strength of our object seeker design. Finally, takeaway. In this paper, we propose object seeker for certifiable robustness against patch hiding attack. We have 2-step masking and box aggregating. And note that the entire pipeline is compatible with any off-the-shelf object detectors. And we have demonstrated a small impact on clean performance and significant improvements in robustness. And we have released a longer version of our paper, the source code, and also we are maintaining a paper list for all the related patch-related research. And feel free to check it out. And that's it for the talk, and I'm happy to take any questions.
Ying Zhicao from Johns Hopkins University. So I have a very great talk. I like it very much. I have a clarification question. So in your example, like the motorcycle example, your patches are mostly like occupy the background. What if it kind of like occupy both the motorcycle and the background? So in that case, if you aggregate those like boxes, will that also cut the patch in half, or it will include the entire patch, which will include more of the background?
I think that really depends on how the model. So I mean, when we mask out something, the model is going to behave slightly different compared to when there's no masking. So it very depends on like, yeah, how the model is going to do. But normally, if say a patch, they partially overlap with the object and also partially overlap with the background, we will still, if the model is good, most of the time, they should just detect part of the object. Maybe like the part that is corrupted by the attacker, we might not be able to cover, the box might not cover that part. But for the remaining part, it's like just, for example, so maybe like half of the object, that should be easy to do for any just off-the-shelf detector. So that's our intuition. But we can discuss offline. And yeah, like there are many tricky corner cases that because the object detector, when we add the masking, some change a bit. But
thank you very much. Interesting work. I wonder if you can talk to the number of patches. So I think your masking procedure may be affected if you have multiple patches strategically placed to circumvent your procedure.
Yeah, so yeah, that's a good point. We have some discussion in the paper, but I didn't talk in the talk. So here we can see that if we consider one patch, our masking strategy. So we have a mask set that can remove one patch. Then the strategy we have, like a very simple extension, is that, yeah, we can kind of combine 2 masks. So we can construct like a new mask set, and each so-called mask is actually like 2 different masks from our original mask set designed for one patch. So just like we are able to detect, so it's just like say one like more generalized version of patch could be, okay, I mask out one part and I mask out a second part. So we can consider that also like a generalized version of the patch, and then we can just directly plug in this mask set to our approach and our certification. They don't need to change. And yeah, so that's how we can extend our approaches to multiple patches.
The last question, maybe.
So do you assume the patch shape is always square, or it could be any shape?
Yeah, so for the, okay, so there is maybe one clarification thing. So our algorithm, just as I discussed in the very beginning, our inference algorithm doesn't have to know anything about the patch shape size, because as we discussed, the only parameter in this example is the number of lines we want to use. We just set the lines, and then it should work for like different shape and size. But here, why? So in this example, why I use like a square or something? It's because in the evaluation, we have to instantiate a particular attack capabilities. Because when we evaluate the attack, we need evaluate the defense. We need to have some specifics about the attack, because we can never have some certificate for like an unbounded attacker. So we need to restrict just for our evaluation. And in our paper, we evaluate, okay, what's the performance for a square patch? Okay, what's the performance for a rectangular patch, for example? What is the performance for a triangle? We all discuss that in the paper. And even we can discuss, okay, what if the attacker can use all different shapes at the same time, maybe different size and place them at different locations? Yeah, our approach can work for that. And all we need to do is just one fixed mask set.
Thank you very much, Chong. And I think there are more questions wanting to ask you. Maybe just put it offline. So
okay, yeah, we can talk offline, of course.
Yeah. So let's thank the speaker again.